All right, welcome back to another math teaching video. Today we're going to be talking about inverse trig functions. So you've likely had a video on trig functions already, the basics of that, how the unit circle can connect to triangles, and then gone over some examples in class. If you want a refresher of that, you can look back at that video. But now we'll go right into inverse trig functions. Inverse trig functions. Okay. So, an inverse trig function. Well, let's start with this. Start with a triangle. Actually, I'll make it. No, that's okay. I'll do this. It's nice isosceles 45, 45, 90. And if I call this pi over 4, this is 1. I can say that, well, the sine of pi over 4 is going to be the y value, which we know from our unit circle. The sine of pi over 4 is root 2 over 2. Now, this is just a regular trig function. An inverse trig function undoes the work that the trig function does. So that is to say, if I take this original function and I take the inverse function of it, I do the inverse of the sine function. So I do the inverse sine of this and the inverse sine of this. I get inverse sine of pi over 4. And then inverse sine of root 2 over 2. Okay. Now, I've just taken this original function here. I can underline these parts in purple. I've just taken my original function, and I've done the inverse sine of both of those components. Now, what we know about inverse trig functions is they functionally cancel each other out. If I have, 7 times x, the inverse of 7 times, right, multiplication is division. So 7 times x, and then doing the inverse, so divided by 7, brings us right back to what we have. 7 times and the divided by 7 cancel each other out. So the same type of thing happens here. The sine and the inverse sine cancel each other out. So you're just left with pi over 4 is sine inverse of root 2 over 2. Or if you want to rewrite it, because we generally have the more complicated things on the left when we're explaining this, we would say sine inverse of root 2 over 2 is pi over 4. So hopefully moving from here to here isn't that bad. You take the inverse sine of both sides, and then you just arrive here. So why is this interesting to us? Well, this is interesting because sine of pi over 4 equals.
How you doing?
I'm doing well.
Hey, Happy New Year.
Happy New Year to you as well.
You moved to CPT, correct?
I did.
Okay, all right. I'm walking through, locking everything up, so when you do leave, make sure that door is closed, please.
Yes, sir.
Thank you. Have a good night.
Thank you. You as well. This is what I get for doing my lesson prep at 10 or 11:30 p.m. on a Saturday. I get visits from security, who are like the nicest people ever. That's good. Okay, so sine of pi over 4. Sorry about the interruption, but maybe that made this video more fun. That's good. Sine of pi over 4 is root 2 over 2. Now, what we're doing here, I'll kind of divide this out. What this is doing is your input is an angle measure, theta, and your output is a sine length. Well, it's really a ratio of sine length. So in this case, right, because sine goes with y, it's really y over r, where r traditionally is 1 in a unit circle. Right, so the output is y over r, which is usually just y, but we'll write y over r. Okay, now, if I write this, the inverse sine of root 2 over 2 equals pi over 4, we should remember back from our work on inverse functions that the input and output switches for an inverse function. Y becomes x, x becomes y. Even algebraically, that's how we solve inverse functions. We switch the y and the x. So in this case, our input is y over r, and our output is theta. So if we are given just the side lengths, and we want to find theta, we can go up. Well, inverse sine of root 2 over 2 is my theta. So I can find my theta. I'm inputting a side length, and then I'm outputting my theta. And then you have function buttons on your calculator that allow you to do this. So you can input any, any y over r, right? This divided by that, and you'll end up with theta as your output. Okay, let's go through a few examples. Example 1, very basic one here. If we have a triangle, and I know all my triangles, well, these two triangles look the same, but that's okay, they're not the same. If this is, let's say this triangle is 0.87, and this is a 1 here. Okay, actually I'll move this down. We'll go 0.87 down here. 0.87 theta and 1. Now, we're not going to use sine inverse, because sine inverse would be to the y over r. We have the x value. So we're going to instead use cosine inverse. So we have cosine inverse of x over r. I hope we can see that the cosine inverse would be x over r, or the sine inverse input was y over r. This is going to be 0.87 over 1, right, which is just 0.87. Cosine inverse of 0.87. And that gives us, in degrees, 60.4 degrees. So slightly above 60 degrees. So slightly above pi over 3. So that, yeah, so this is 60 degrees. And that's really it. That's really all there is to this. I can do another example. I'll do an example 2. Just to show you this could work with anything. It works with any triangle. Trig and inverse trig can work with any right triangle. Example 2 here, just a basic one. Oh goodness. Get your triangles. Here we go. There it is. There it is. Let's say we have this is 3 and this is 6. Right, then we would have cosine inverse of x over r again, so 3 over 6. All right, so that's cosine inverse of 1/2. And if you think back to the unit circle, what angle measure gives you a cosine value of 1/2? Right? When is that x value 1/2? And that happens at pi over 3. Yep. And that just comes from the unit circle. So this theta is pi over 3. And if you plug it into the calculator, you'll see that this is pi over 3. It's going to be, 1.04-ish in radians, and in degrees this would be 60 degrees exactly. Okay, good. Those are the 2 examples. Now, we've discussed the inverse of sine, we've discussed the inverse of cosine. Let's talk about the rest of the ones that we get. Erase all this. Now, we have, just like we had 6 trig functions, sine, cosine, tangent, and then the reciprocals. For sine, it's cosecant, for cosine, it's secant, and then for tangent, it's cotangent. We have 6 inverse trig functions. And it works, hopefully, as you'd expect. You have sine of theta equals y over r, and that becomes your original trig function. Your inverse trig function is sine inverse of y over r equals theta. Here you have cosine of theta equals x over r. So cosine inverse of x over r equals theta. Then you have tangent of theta equals y over x. So inverse tangent is, inverse tangent of y over x equals theta. Then you have the other 3 that pair with this. We don't use them a lot traditionally, so I'll just leave these here, and then just recognize that it's the same pattern for the other 3. and the domain restrictions we're about to write up, the domain restriction for sine follows the domain restriction, or it's followed by the domain restriction for cosecant. Okay, but don't worry. In this section, we're not going to be talking much about inverse trig for the reciprocal functions for the 1 over sine, right? Or inverse cosecant, inverse secant, inverse cotangent. So there are 6 of them, but in reality, we only really talk about 3 most of the time. The other ones, if you get to them, we can talk about those in class. Okay, so these have domain restrictions. And really the issue with the domain restrictions isn't that, the domain is going to be almost implied, right? I mean, y divided by r is traditionally 1. The largest the sine value can be on a unit circle is 1, right? It goes from -1 to 1. The question becomes, what does this mean for the theta? So it's almost a range restriction more than anything else. So in this case, and I'll write this up and explain it, the range is between -pi/2 and pi/2, okay? And we'll work through this down here, just because there's space. Here's what we mean by that. If I have my unit circle, and I say, okay, at which theta do we get a y value of 1/2? Well, you get that here, and you get that here, right? This is 1/2, this is also 1/2. But you can't have both. You can't have, if I say, okay, what's the inverse sine of 1/2, you can't say both pi/6 and 5pi/6, then it's no longer a function, because you're having 2 outputs. You're saying it is both pi/6 and 5pi/6, and that breaks the definition of a function. The definition of a function is for any one input, there is no more than one output. So in this case, you want to restrict the domain such that you're hitting all of the possible values for sine, but you're only doing it once. So we restrict our domain to go from here, our range, we restrict our range to go from here to here. And this way, we cover every value of sine, right? -1 to -√3/2 to -√2/2 to -1/2 to 0 to 1/2 to √2/2 to √3/2 up to 1. And there's only one output associated with each side length, right? In this range, there's really only one place. There's only one place where the sine value is -1/2. It's right there. Okay. So that is why the range gets restricted. Otherwise, we would have something, oh, we want the sine inverse of 1/2. That happens here and here. And then you have 2 outputs. You have 2 theta values. And we want to restrict this so there's only one. Okay, so we restrict the range to -pi/2 to pi/2. Now, I did the same type of thing for cosine, where the range restriction for cosine is 0 to pi. And then for tangent, the range restriction is -pi/2 to pi/2. It follows the same logic if you draw it on the unit circle. The reason why these are exclusive is because, what happens when it's -pi/2? When the theta value is -pi/2 for tangent, it doesn't exist, because at pi/2, you're here, vertical, and your x value is 0. So you can't have anything, you cannot have anything here for tangent, because you're going to have 1 divided by 0, right? So saying that the theta for tangent can be associated with pi/2 or -pi/2 just doesn't exist, because that point doesn't even exist within the tangent itself, because you have 1/0 or -1/0 for the -pi/2 part. I hope that's okay. We can talk about that in class, so it's a little bit confusing. Okay, last thing to discuss here. Is the composition of trig functions. I'll give myself more space. Composition of trig Composition of trig functions. All right, so let's just go over a quick example. We'll do two. Example one, what is the cosine of the inverse sine of 1/2? Okay, well, what is the inverse sine of 1/2? With the domain restriction we just wrote up, side length of 1/2 gives us what theta value? It gives us pi over 6. So this is really just pi over 6. Right? So I'm not taking, think of cosine, not of this thing, but just think of cosine of pi over 6. And what's cosine of pi over 6? This goes back to original unit circle. Cosine of pi over 6, if you look at the triangle. Okay, if that's pi over 6, that's 1. Cosine of that is 1/2. That's a lie. That's the sign. It's that right here, 1/2. There we go. I'm lying again. Cosine is root 3 over 2. Good. I'm glad I caught myself. Cosine is root 3 over 2. Yeah, cosine, the x value associated with pi over 6 is root 3 over 2. Good. The y value, which is the original input to the inverse sine, that's 1/2. Sorry about that. Good. All right, so that's example 1. Now, we'll do a separate one. This will be composition of trig functions where you're actually asked to write everything in terms of x. Okay. So let's say we want to write sine of cosine inverse of just x as an algebraic expression for x. So what's happening here? Well, if we were to draw this, we know that the cosine value, this input here is not theta, this input here is a side, right? So we're saying the side is x and it's the cosine value. So this becomes x, right? And, let's just say that this is 1 for the sake of it. That's what we tend to use. So what's over here? Call this thing y. Well, because that's what we want, right? If this is theta, we want sine of, this theta, which is given to us by the inverse cosine of x. So what's this y? Well, we can use the Pythagorean theorem and say that 1 squared equals x squared plus y squared. So when you subtract the x squared over and take the square root, you end up with y is 1 minus x squared and the root of that. Okay, so that's what you're given here, right? That becomes y. So over here you have the square root of 1 minus x squared. And now the question is, what is the sine of, remember this? What is inverse cosine of x is the theta measurement. Remember we had cosine inverse of x over r equals theta? That's telling us that the cosine inverse, when you input the side length, is theta. So we want sine of theta, right? We're getting sine of theta, and what they're telling us is they're describing a little bit of what what this triangle looks like. It looks like the cosine inverse, it looks like the x value is just x, right? You're plugging in an x to cosine inverse. So this thing is just x. It could be anything. It could be elephant. It could be 7. In this case, they just give it to us as x. And then we say, okay, what's the sine of that? Well, the sine of that is going to be the associated y value. Technically, it's y over r, right? It's y over r. Sine is y over r. But the r is 1. So it's just going to be this. This whole thing, sine of cosine inverse of x is just, it's y over 1. It's the sine of this, so y over 1. So it's just going to be root 1 minus x squared. And that's it. Okay. So we're getting into the weeds a little bit of trig and inverse trig. I think we'll be okay. And if you have any questions, you can email me or text me or find me. I'm happy to meet with you, and I look forward to seeing you all in class and in the next video. Thank you.